So I am my current affiliation is my main affiliation is with the Breakthrough Institute. So I'm co-director of climate and energy there, and I also am an adjunct faculty at Johns Hopkins in their energy policy and climate program. And I have this third affiliation with San Jose State's Wildfire Interdisciplinary Research Center, which is where some of the research I'm going to be talking about today comes from. So the title of my talk is "Do Climate Adaptation Strategies Get Enough Attention? The Case of Wildfires in California." And so this talk is going to be broken up into two distinct parts. So the first part is basically a science part, so a specific adaptation strategy for wildfires in California. And so that's exemplified by this preprint that we have called "The Potential for Fuel Reduction to Offset Climate Warming Impacts on Wildfire Intensity in California." And then the second half of the talk is this "Get Enough Attention" piece. And so I'm going to be talking about some points that I brought up in a piece that I wrote in the Chronicle of Higher Education called "Does High-Profile Climate Science Tell the Full Story? Social feedbacks and career incentives cause scientists to leave a lot out." So this is kind of a meta science, sociology of science commentary. So first, with the science side of things, climate adaptation strategies in the context of wildfires in California, you can kind of tell from the title of this paper that we basically know that there's kind of two main drivers that California wildfire risk and danger is increasing. And two main drivers are the accumulation of fuel, so vegetation in our forests, and climate warming. And we're looking at kind of weighing those against each other. So the climate change component of this is mainly, the main mechanism is just that as it's getting warmer, it's drier over land in the summer when there's not precipitation, and that dries out fuels and makes combustion happen easier. But the other component of the increase in fire danger recently is fire exclusion. And so fire exclusion is kind of shown by these pictures here. This happens to be a forest in Montana, but a lot of forests in California look very similar. So this is 1909, 1948, 1989. So post-colonization, the federal government implemented a policy of fire exclusion. So indigenous people and kind of the natural fire regimes in the area were such that wildfire frequency was something like once per decade, and it would kind of come in and clear out, wildfires would come in and clear out a lot of vegetation. But in 1912, that was put an end to by the federal government, said no more fires. And in 1935, the 10 a.m. rule was put in place, which means that all fires should be put out by 10 a.m. the next morning. And so what that meant is that areas that previously were experiencing wildfires every once per decade about had not been experienced fires for over a century. And so that's caused fuel, vegetation, to build up in the forests. And when we look at metrics like area burned, we can see that at first this kind of worked. So this is in the 1910s through recent times, area burned in the whole Western US. And so this fire exclusion policy initially, worked if the goal was to have no fire in the landscape. And so by the 60s and 70s and 80s, we had this minimum of area burned annually. But as you can imagine, you're basically creating a lot of potential energy. It's like you're kind of stretching a rubber band by leaving all of that vegetation on the surface. And so then you have warming conditions coming in on top of that. And so then we've had this situation of increased fire danger and increased area burn since the 1980s. And so in addition to there just being more fuel in the landscape, there's other reasons why more vegetation is more conducive to fires. So one is that the ecosystem just tends to be more sensitive when there's more vegetation, and that's because of competition for finite resources. So there's only a finite amount of sun, a finite amount of nutrients, a finite amount of water. And if you're spreading that amongst a larger population of plants, then each get less. And so then when you have a drought, the entire ecosystem is more sensitive to that drought, and disease, the entire ecosystem can be more susceptible to disease. So other reasons that more fuel can be worse is that when you have a fire with more fuel, it can burn more intensely. And so that means that you can have like much hotter, faster updrafts in the fire, which then bring in oxygen, the main fuel for combustion, on the sides of the fire. And so these are plume-driven fires, they're called. They can create their own weather and then be very erratic and difficult to fight because they're being steered by the winds that they themselves are creating. It's also harder for firefighters to fight fires in densely packed forests because it's literally harder for them to access them, or it's harder for uh, um, flame retardants to access the fires. Uh, Fires in forests that have a lot more, that are more heavily stocked, produce more smoke, which is a huge detrimental impact to human health, and they produce more ash, which contaminates water supplies. And finally, if you have a more stocked forest, you're more likely to get these crown fires. So a lot of these fuels are called ladder fuels, which means that you can, climb up into the canopy of the forest, and that's where you can do the most damage to a forest and potentially kill the entire forest. So what's the solution to this? The solution to this is to proactively remove fuel from the landscape. And so this is what this looks like in a couple of landscapes. On the left is a more brush landscape. On the right is a forested landscape. And so you can do this in a couple of ways. You can do this with what's called mechanical thinning and or prescribed burning. So mechanical thinning is you're literally going in with machinery or hand tools and pulling out vegetation. And then prescribed burning is when you intentionally light the surface on fire during conditions when it's very unlikely that that's going to break containment and you have fuel breaks around. But you do it in the spring or during times when it's cooler and more moist, and so that fire will not be incredibly intense. And so we basically know that this works, and it essentially works like this cartoon. That kind of decades of on-the-ground firefighting experience has showed this, that when you have a overstocked, untreated forest, when the fire comes along, kind of everything burns, and you have widespread tree mortality post-fire. Where if you've done this mechanical thinning and prescribed burning ahead of time, a fire comes in and it stays low intensity, it stays on the surface, and then post-fire you still have a forest. And so that's what it looks like in a cartoon theoretical sense, but we see this in real fires. So this is the Boot Lake fire in Oregon, where in the background you had a fire that went through a no treatment zone, so no mechanical thinning or prescribed burning. And then in the middle ground, the same fire did transverse this area, went through a thinning and prescribed fire region. And then in the foreground, we have a thinning only situation. But so in the background, we see widespread tree mortality. In the middle, the forest has come away largely unscathed. And then in the foreground, thinning only is showing that that's not nearly as good as thinning plus prescribed burning, because you want to remove those fine surface fuels, which is what you get with the prescribed burning. And so those are kind of like anecdotal pieces of evidence, but this has been studied by tons of studies over the years and summarized by meta-analyses. So here's a meta-analysis of those studies of thinning, prescribed fire, and wildfire effects on subsequent wildfire severity in conifer-dominated forests in the western US. And so their main result is we found overwhelming evidence that mechanical thinning with prescribed burning, mechanical thinning with pile burning, and prescribed burning only are effective at reducing subsequent wildfire severity, resulting in reductions in severity between 62 and 72% relative to untreated areas. So this knowledge has gotten into syntheses of scientific studies. So here represented by the California's fourth climate change assessment, fuel treatment for forest resilience and climate mitigation, a critical review for coniferous forests in California, where the first two highlights of the executive summary of that report are basically saying that this works. So fuel treatments that use a combination of thinning from below and prescribed fire or prescribed fire alone with adequate consumption of surface fuels and increased crown separation, so the canopy of the forest, have been shown to reduce fire severity within and adjacent treated areas. So we know that this works. We know what direction this works in, but the topic of this research that I've been conducting is basically how well does it work, and what's the potential for it to offset the impact of climate warming on wildfire intensity is what we're looking at in California. And so we take what's out there and take kind of the next step in a bunch of different dimensions. So this study is kind of a novel and, to my knowledge, unprecedented combination of number of observations. So we have 27,000 satellite observed observations of wildfire intensity. It's very granular in terms of the number of attributes of fuel characteristics we're looking at. So 10 different surface fuel characteristics, high resolution in space and time, so 0.5 kilometer resolution in space and hourly resolution in time. We have a large extent of our data set, and then we're using machine learning to quantify the relationship between all of these conditions and subsequent wildfire intensity. So there's basically kind of 3 steps to this research. There's one is learn the relationships between environmental conditions and wildfire intensity. 2 is extrapolate in space, and 3 is make future projections. So the first one, just learn the relationship. So again, we have 16 environmental conditions, and we have, for each one of those, we have observation of wildfire intensity, and we're using neural networks and random forest models to connect those predictors to that predicand. And so this is very useful to use these flexible machine learning models in this context, because a lot of traditional regression methods like either assume linearity or they assume monotonicity with predictors in the predicand, where no matter what, there's going to be like an increase in a predictor is always going to have the same sign effect on your predicand, where this is allowing that full dimensional, like 16-dimensional space to be explored, and it allows for the influence of any one predictor on the predicand to be highly conditional on the state of the other predictors, which is what physically we know to be the case with wildfires. So once these models are trained, then we extrapolate in space. So what we do is, now the models, given environmental conditions, will make predictions for wildfire intensity. And so we always have environmental conditions, so we can make maps of predicted wildfire intensity if there was a fire in that location at that time. And so this is what these look like. We call these fire intensity potential maps. So this is for a time period that was particularly consequential. This is September 8th in the afternoon of 2020, when wildfires were blowing up in the state of California. And so this is just showing, spatially where the models predict the most risk was. And then the next step is to make future projections. So what we do is we take these maps, these instances of conditions that were very conducive to wildfires, as well as kind of random conditions, and we place them in future climates with and without fuel reduction. So we have kind of fuel reduction scenarios as well. So climate scenarios and fuel reduction scenarios, and see how this fire intensity potential changes. So here's just some examples of different weather snapshots that we're then placing in these different conditions. And so here is the summary of what you get when you do that. So we have 3 different time periods. So there's basically a current time period, a mid-century period, and a 2090 period. And this is all pinned to the current period. So this is for the 30 most extreme hours in our data set. On average, what this is saying is that the fire intensity potential for the entire map was about 560 megawatts. And so then we're going into the future. This is just changing the climate. So it's changing the temperature, which then changes the fuel aridity. And we have 2 different emission scenarios here. So there's a 4.5, like SSP2 4.5 emission scenario, and a more Paris compliant SSP1 2.6 scenario. So I'm labeling that slow emissions reductions and fast emissions reductions. And so what we see here is that as it gets warmer and drier, we're seeing an increase in fire intensity potential. But the difference between the emission scenarios is not that much. So especially by mid-century, you're talking about, under slow emissions reduction scenario, plus 14% relative to today. And under a faster emissions reduction scenario, you're just knocking off 2% there. And they differentiate a little bit more in the future, plus 25, or at the end of the century, plus 25% versus plus 16%. But what if you were to scale up fuel reduction? So now we're getting like a big differentiation. So this is if you were to do fuel reduction on 1.6 million acres per year, targeting the areas that have the largest influence. And that's 3% of the domain. And it's not actually, this is not like a crazy number. So 1.6 million acres per year compares to what the state's articulated goal right now for starting in 2025 is to do 1 million acres a year. So this is, 60% more than that, but it's, in the ballpark. It's, in the realm of possibility. And so what we're seeing here is now we're below this, 100% line for the entire rest of the century. So you're getting more than a 10% reduction in fire intensity potential by the mid-century, and even by the end of the century, you're below where we are presently. So what we're seeing here is that there's a bigger difference in scaling up the state's policy of fuel reduction. That makes a bigger difference than scaling up the global ambition for greenhouse gas emissions reductions. And that even in a situation where you have slow emissions reduction, so that RCP 4.5 scenario, you could still have a future of reduced fire intensity potential by the end of the century relative to today. So it's not just a situation of like it's going to increase, but it would increase less with fuel reduction. You're offsetting some negative impacts. You're actually getting less relative to today. So I think that's good news in terms of these results. Does this get enough attention? So, I think this. I'm biased. This is my study. I think this is pretty cool. But I'll note that this has been having a hard time getting published. So, I'll just say this has been rejected by kind of all of the high impact venues. So Nature, Science, PNAS, Science Advances, PNAS, Nexus. And so we wouldn't, necessarily expect all of our studies to be published in Science and Nature. But I will contrast this to the previous iteration of this research that I wrote a paper on that was accepted by Nature. And even before these rejections, this paper, after I published this paper, I published a essay in the Free Press, basically critiquing this paper and critiquing the framing of this paper, basically saying that the framing of this paper was kind of designed for it to be palatable to a high impact publication, and that was not the most useful way to frame the paper or to frame the research. And actually, I think this is the much more useful way to frame the paper, frame the research. And I can tell you that the difference between these two papers is definitely not that this one that's having a harder time being published is worse on any technical ground. So it's much better on basically all technical grounds. So it's better. I have this table here basically showing that it's better on kind of 17 different dimensions. There's more data, higher resolution. It's simultaneously more sophisticated and more elegant in its methods. And so that brings me to some of these points that I bring up in this Chronicle of Higher Education piece, which is basically that I think that the difference between these two papers is the framing, that this paper was framed to look, exclusively at this climate change impact, and that's what made it more to focus narrowly on a negative climate change impact, and that's what made it more palatable to a high impact journal. So in this piece, I make a number of points, and I'm going to kind of go through them here. So the first one is just that there's substantial incentives to publish in high impact journals, and so I make the argument that the highest return on investment from a researcher's perspective, if you want to publish in these high impact venues, is to frame research that at least directionally is kind of in support of the Paris Agreement or in support of these temperature targets. And so there's energy researchers and climate impacts researchers, but if you're on the climate impact side, that manifests itself as seeking out and highlighting negative impacts of climate change. And it means that you kind of want to frame your study at the end so that the independent variable is emission scenarios. You're kind of like looking at an outcome as a function of emission scenarios, and you're basically saying the outcome is bad under high emissions and it's much better under lower emissions. And so I think these incentives basically shape the aggregate output of the high impact literature, which then shapes public knowledge and decision maker knowledge. And I argue that it's overly focused on emissions reductions as a solution to problems. And that's at the expense of more actionable adaptation options. And it also sidelines legitimate concerns about overly restrictive energy policies, especially in low-income countries. And I think that that's important when you consider that energy undergirds a lot of the kind of successful adaptation that we've seen historically. So just kind of going through these, and I'm going to try to go quick now because I'm behind, but just to kind of establish that there are substantial incentives to publish in high impact journals like Nature and Science, of course, being the most emblematic of that. The first is just that high impact papers, get the most attention. So in my piece in the Chronicle of Higher Education, I do a couple of literature reviews. One is on the papers that get the most attention. And so the 50 climate change papers that received the most online attention over the past 5 years, 64% were from Nature and Science, and 86% would be from what would be considered high impact journals if you consider PNAS and the Lancet. So it's pretty clear, where you want to publish if you want your papers to get attention. And that's, there's attention for attention's sake, but there's also, direct career influence on that. And one of the influences is just citation count. So, as researchers, we're judged not so much on raw paper count, right, but by citations and H indices and things like that. And so the increased attention is what gets the papers in front of the eyeballs of other researchers, which then makes them more likely to cite your research. And I've seen that with my own publications, that my previous paper that was in Nature from 2017 has over 5 times the citations of the next paper on the list is from a more disciplinary journal. And even this wildfire paper that was controversial because I critiqued it after the fact, this will rapidly be like my second most cited paper. So it'll go like Nature, climate change. So it's like clear, from my own personal perspective, like where you want to publish if you want to, have citations, which boosts your quantitative metrics as a researcher. So that's like a kind of an indirect effect, but this has been shown to directly affect the careers of researchers. This has been discussed in the pages of Nature. Why does a high impact publication matter so much for a career in research? Where they note that early career researchers, when they're applying to faculty positions, are about 6 times more likely to get the position if they have a lead author paper in a high impact journal. And then once you are a faculty, whether you're promoted or not, from assistant professor to professor, is also impacted by whether or not you're publishing in these venues. So this is use of journal impact factor in academic review, promotion, and tenure evaluations, where they conclude that journal impact factor is encouraged in review, promotion, and tenure evaluations, and that's corroborated by other research as well. So what that means, because there's a lot of incentive to publish in these journals, it means that these journals can be highly selective, right? So Nature accepts about 8% of submissions, and Science accepts about 6% of submissions. And so that means that editors, they're receiving a flood of submissions. And so they're acting kind of as the bottleneck. And it means that they have a lot of sway on what's produced by the journals and then what gets the most attention. And it means they have a lot of sway on public knowledge and decision maker knowledge. And it means when this is such a competitive area, it means that researchers have to think carefully about formulating their research so that it stands a chance of publication. And so we see that, with the whole cover letter process. This is what it says on Nature journals. When you submit a cover letter, it's your chance to sell your research, to the editors, right? Because you want to tell them that it's high enough impact for the journal, worthy of enough attention. And also, you're going to be selling that it's something that's kind of palatable to the journal. So you can, look at the covers of the journals to see what's palatable. That would be one strategy. But of course, you're not just going to start selling your research as a researcher at the point of submission. You're going to start, thinking about that at the outset, at the very, conception of the research and the research question. And so, researchers thinking about this, what is going to be the highest return on investment? So I'm arguing that it's to frame research that at least directionally is in support of the Paris Agreement. And I think that you only need to listen to the leadership of the journals to see this. So this is an example of messaging from the leadership of the journals. This is Dr. Marcia McNutt, who was the editor-in-chief of Science, when she wrote this editorial in Science called The Beyond 2 Degree Inferno, which is very much in support of the 2-degree temperature target. It's very passionate. She uses words like sinners to describe human behavior. She says, "I wonder where in the 9 circles Dante would place all of us who are borrowing against this earth in the name of economic growth, accumulating an environmental debt by burning fossil fuels." So to me, this signals to researchers that science is going to be more sympathetic to research framings that center emissions reductions over research framings that might center climate resilience or adaptation successes, because that's going to be considered kind of a cross purposes or mitigation deterrence, like less motivation to reduce emissions. Similarly, Nature has done things like officially endorse as an institution Joe Biden for president, for reasons including climate change reasons. So on climate change, Biden would return the United States to the Paris Agreement and is proposing the most ambitious domestic climate policies ever advocated by nominees from a country's major party, from the country's major parties. So again, this is signaling to researchers that they might be more sympathetic as an institution to framings that center emissions reductions as kind of your main knob there. And so Nature got some pushback for officially endorsing Joe Biden, but here is Holden Thorpe, the current editor-in-chief of Science, defending that endorsement and basically saying that Nature and Science should endorse policies and politicians because if they don't do that, that gives people permission to say things like climate change may be real, but I don't think that we should have government regulation to deal with it, which is unacceptable. So to me, I mean, this is kind of showing a very authoritative, frankly, kind of illiberal attitude about science. But regardless of that, it's basically signaling to researchers that there's going to be, some research framings that are going to be more palatable to the journal than others. If researchers want to, conduct their research in a way that's going to be palatable to these journals, how do they do that? So I would contend that on the climate impacts side of things, it's basically seek out and highlight negative impacts from climate change. And it's kind of this subtle thing of just how research questions are framed. So it's basically, don't ask this question, ask this question. So rather than ask, what is the magnitude of the influence of climate change on the phenomena I'm studying relative to other relevant influences? It's more prudent to ask, how does climate change negatively impact the phenomena I'm studying? And this is exactly the dichotomy of these two papers that I've written. So one is having trouble getting published, at least had trouble at high impact venues, and one did not have trouble getting published. And so I think this is basically a systematic problem of framing research questions this way. How does climate change negatively impact the phenomena I'm studying? And so I'll just give a couple other examples, and I'll take examples from this paper. So I'm going to use examples that are like the two impacts on people that are calculated to be the largest. So this is a paper published in Nature, Comprehensive Evidence Implies a Higher Social Cost of CO2, where they break down the total cost of carbon into sectors and identify that human mortality and agriculture are the two sectors that are the largest contributors to the social cost of carbon. So I'll just use an example from both of these. So first, human mortality. This is a paper published in Nature Climate Change called The Burden of Heat-Related Mortality Attributable to Recent Human-Induced Climate Change. So, I mean, we can tell right at the outset here that this is just, heat-related. So that's obviously going to be the thing that's the negative impact from climate change. But it's actually known from the same literature that deaths from cold actually outnumber deaths from heat by quite a large margin. So globally, something close to 9-to-1. And so even when you just calculate warming by itself and its effect on mortality, the research that uses the same data has found that net deaths, historically at least, have actually been decreasing because cold deaths have been decreasing faster than heat deaths have been increasing. So I think that's an important, omission here, because there's no equivalent paper that's just on cold-related mortality. But even isolating the heat deaths alone, in most locations, deaths have been decreasing over time despite warming. And so here's how the IPCC puts it in Working Group 2, Chapter 16. Heat attributable mortality fractions have declined over time in most countries owing to general improvements in healthcare systems, increasing prevalence of residential air conditioning, and behavioral changes. These factors have determined these factors, which determine the susceptibility of the population to heat, have predominated over the influence of temperature change. So this is a really important result because we want to double down on whatever success is undergirding this. But that is kind of swept under the rug with this research framing of how does climate change negatively impact the phenomena I'm studying. And I'll just give another example of agriculture here. So here's another paper in Nature Climate Change. Anthropogenic climate change has slowed global agricultural productivity growth, where the main finding here is that agriculture historically has gotten 89% more productive in terms of total factor productivity. So that's like the value out per value in. But what they're saying is that were it not for climate change, then it would have gotten 110% more productive. But to me, framing the study this way, agriculture or anthropogenic climate change has slowed global agricultural productivity growth, it diverts attention away from what's causing, all of this success, and it makes it harder to understand that and repeat that. So that's for the two largest impacts on people: mortality and agriculture. But I think you see that in other areas as well. And so for both of these situations, like adaptation might be a situation where the climate is changing, but we're adapting such that the outcome is staying the same as the climate is changing. But both of these situations you might call super adaptation, where the climate is changing, but other dynamics are changing such that the outcome is getting better over time, despite the fact that the climate is changing. And I think that that's important to highlight so that we can understand it better. And it's not good to divert attention away from that. So those are, specific examples, but in my piece in the Chronicle of Higher Education, I take a more systematic approach and look at this in a literature review setting. The top 50 climate change papers is ranked by Google Scholar from Science and Nature in the past 5 years, and just kind of like look at these patterns. And you'll find that in that, the majority are framed that kind of at least directionally support the Paris Agreement, and very few studies in there adopt an optimistic tone leaning into historical increases in human resilience to climate, which are really ubiquitous if you look for them rather than looking for the negative impact. And a lot of studies use very pessimistic and warning-oriented languages around climate impacts, but no studies use pessimistic or warning-oriented messaging around overly stringent restrictions on current energy or agriculture systems, which is really important because those are the systems that are undergirding a lot of this adaptation success. So I have some suggestions for ways I think might help reform the system. So I think the main thing is that we want to push back against this component here, that the highest return on investment is to frame research in support of a policy that exists, and to seek out and highlight negative impacts of climate change. So one thing that I think is kind of a no-brainer that has started to be adopted by other fields is pre-registration. So, that's where papers are accepted based on the research questions alone and the proposed methodology, so not on the results. And I think that would help induce more neutral research questions about the underlying drivers of various things, rather than, at the outset deciding what your target variable is and kind of framing or molding your research around a preordained outcome. And so that would, essentially reduce the impulse to adjust research questions and methods in order to increase the likelihood of a high-profile publication. And I'll add two suggestions that I got from this paper called Pro-Social Motives Underlie Scientific Censorship by Scientists of Perspective and Research Agenda. So one of their ideas, which I think is good, is to publish reviews and editor decisions for rejected manuscripts. So it's becoming more common to publish reviews and editor decisions for accepted manuscripts. But if you want to study what's left out of the literature, which is kind of what I'm concerned about here, then you also want to publish the rejection letters. And so that would make that easier to study. And so along those same lines of studying editor decisions and journal decisions, I think journals should embrace audits that test for bias. So like a third party submits two versions of a study to a journal with the same methods, but different results, manipulated results, to see if methods are scrutinized differently or treated differently depending on the results. So I think that would go a long way to be able to studying the phenomena I'm talking about. And ideally, what would happen is that you'd have metrics of essentially journal non-bias that journals would wear as a badge of honor. Where right now we have metrics of impact factor is the main way that journals advertise themselves. And so if you had we score a 10 on our non-bias auditing, then that would be, I think, helpful culturally. And so this is my last one. So there's these special issues and op-eds soliciting research in support of the predominant narrative. And some of these special issues are actually sponsored by third-party foundations and things like that. So that's another question of whether we want foundations sponsoring special issues in in journals. But so anyway, we've seen that. And so why not special issues and op-eds, kind of soliciting research that's kind of outside of what has become the predominant narrative. So specifically research that's highlights successful resilience to climate in order to foster more of it, of course. And maybe even we should just have like a whole journal. So I've been picking on Nature Climate Change here. And maybe it's fine, Nature Climate Change can be the negative impacts journal, but then there should also be like a Nature Climate Adaptation or Nature Climate Resilience, where some of this research that I think is underrepresented could find a home. And so I think that that would make that research better known, better understood, more repeatable. And it would mean that it would be easier to actually implement things like fuel reduction to offset climate warming impacts on wildfire intensity in California. Thanks.